it a try. Hope you had a good weekend. We might as well get going now since it's officially, oh, it is 32 after. The picture that you see up here on the board is might be kind of confusing, but this is one way to talk about functions. You've dealt with functions, with formulas and stuff like that. Our topic for this week is functions in the area of discrete math, and all that really is mapping from one set to another. Yeah. That's what you do in algebra as well, is just that there you're typically talking about the set of real numbers to the set of real numbers, two infinite sets. So drawing a picture like this is not as important. But for computer science purposes, what we might do is we might map from a set of students into a set of classes, or from a set of classes into a set of students, or from a set of faculty into a set of classes, or other things like that. So we're using sets of people or topics or classrooms or other things like that, and we're simply saying that there is a relationship between elements of one set and the elements of the other set, and that relationship is the function that we're using. Functions do have one other thing that separates them from the general idea of a relation, and we'll talk about that. We're going to talk about relations in general later on, and we'll look at some different properties of them. But right now, we're going to be looking at functions. So the relations come 5 weeks from now, something like that. Let's get going here. So our topics for today, first of all, we had sets last week, so of course we need to have a review, just a quick one to make sure that we get everything done there. Introduction to functions, to way of representing functions, and we'll talk about the different methods that we can use to do that. We actually have a program coming up where we will be entering functional elements as a set of ordered pairs. So you enter the element from the first set and the element from the second set, separated by a space, and those become the elements of the ordered pairs. So we're mapping from the first element to the second element. It'd be like X would be the first element and Y would be the second element. Let's talk about our sets now. What is a set? I'll give you the first word, or two words. A collection
of unique items.
The unique things and repeats, we just have to make sure that there's only one of each thing. So the set of integers, we don't have two twos. We have a -2 and a +2, but those are two different things because the negative sign gives it a different meaning. Our notation is that we use an epsilon and a little epsilon to tell whether or not one thing is an element of something else. By convention, we usually use lowercase letters to talk about the elements, and uppercase letters to talk about the set itself. The set would be named by an uppercase letter. We talked about some special sets. The overstrike representation of them are N is the set of
natural
numbers, and that includes, I don't know, the ones that aren't not natural, the synthetic numbers. But it's actually, you can view it as counting numbers. You know, how many bananas do you have in the desk in front of you? So we start counting with that. Nobody in here apparently has a banana in front of them. We start counting with 0, and then we move forward from that. There are other texts that may actually represent the set as just equal to the set of positive integers, but for our text and our purposes, we're going to call it the set 0 through infinity of integer values. So non-negative integers. The Z, like catching Z's in class.
Set of integers.
Yeah, it's the set of integers. We use Z for integers. I'm not sure why they didn't use I, except that I would probably mean imaginary. Except here we're using C for complex, meaning imaginary. Z plus then would be the positive ones. Q would be the the rational numbers, and we don't use an R there because R is for real numbers, and rational numbers are quotient. We have a numerator and denominator, both of which must be integer values. So that's kind of the idea there. And then real numbers and positive reals, and then finally our complex numbers, where we have an imaginary real part and an imaginary part. Well, you'll often see set builder notation. Yes, no question. Yeah, I used to have hair once, so I could play with it. But here, the set builder notation is something that you need for your 2899 exam. You need to be able to understand what it's talking about, and we're just saying that we're talking about a set composed of elements from another set that is constructed or built using a restriction on the element on the sets. So here, for example, be talking about the set of real numbers where it is all those real numbers such that 4 times the number is an integer. Can you list a couple of those numbers for me? 0, obviously, would be 1.
1/4.
Pardon me?
1/4.
1/4, 0.25. 1/2, 3/4. Anything, so it'd be 1, or 0, 0.25, 0.5, 0.75, 1, 1.25. So it'd be real numbers where everything is separated by a fourth. And it starts at 0 and just goes on positive and negative from there. So we'd be restricting or building our set based off of the elements from the real numbers and using that restriction or the property that 4 times that number would be an integer. Oh, my arrow didn't work there. Sets can contain other sets. Here's an example. It's got elements 1, 2, 3, 4, the set 4, 5, and the set AB. So it's got 5 elements, 2 of which are sets, 3 of which are not. We could have a set that is, let's see, like all the cookware or all the things in my kitchen would be like a set of china. Well, not really china. Set of flatware. No, and then you could probably do that. So a set of flatware would be one of the things. I might have one coffee maker, one bread maker, an oven. There could be individual items, and that's what we have here with 1, 2, and 3. And then there could be sets of items, like the flatware set could contain forks, knives, and spoons. So that's the idea, is that a set can contain other sets. Like, most people have multiple clothing items, and you don't usually enumerate them. You say, yeah, that's my underwear drawer. You don't enumerate each individual piece of underwear. So that is a set, as opposed to your favorite shirt, which may have, well, the one I wore for my kids was Finding All Your Faults, Just Like Mom. And that was kind of a tongue-in-cheek thing, but I wore the heck out of that shirt, but I only had one of them. So I didn't have a set of favorite shirts. I had just a single shirt. Actually, the other one I liked better was the Resist Conformity, 1791, the Bill of Rights, that kind of thing. Anyway, B here is another one that just happens to contain. The first one, we have sets that contain integers and letters, and the second one is all integers, but it doesn't really matter. The power set was another set that we talked about. And we said 2 sets are equal only if their elements are exactly the same. So if I have a set containing a set 1, 2, that is not the same as the set 1, 2. So important thing, they'll probably trip up some of you on quizzes or an exam, so just keep that in mind. We also have the empty set, written as a phi or curly braces with nothing in it. And then we had a representation that was different than simply listing all the elements. We could call that a Venn diagram. We had the funny one with all the different kinds of food. And the universe is the box around it. Sometimes people will draw it without the box. The universe, we're just limiting the things that could be in it. So, or saying that there's a boundary. There might be some things from which this set is not taken. So, but that gives us the ability to represent that concept, that there's a universe that we're drawing these sets from, and then we use a geometric figure to draw them. So if all the elements in A are in set B, set A is a subset. And note that this is got the equal sign. All the elements in set A could be in set B, but we could also have the case where all the elements of set B are in set A, in which case we would say that they are equal. And we write that with an equal sign. And then if one set has more elements, then we say that it's bigger. And we talked about the cardinality being using the vertical line. We're going to be using the vertical line a lot for, it's for set notation, it's the cardinality. For computer operations, it's an OR. And then, of course, once we get to integers, then we're going to be talking about absolute value kinds of things. The empty set has a cardinality of 0, and as a result, it's a subset of every other set, because everything in the empty set is in another set. Nothing is in everything, I guess, is kind of the key there. And then the set, the Cartesian product was the last thing we talked about. Databases are not quite the last thing, but close. Databases are based on this idea, where I've got different sets and I draw elements from them. A relational database is essentially a Cartesian product of multiple sets. So, if with two sets we call them ordered pairs. For multiple sets we call it a tuple, and it would be an n tuple, or if we have a specific number, it could be like when we get to languages or talk about Turing machines, if I remember correctly, are a 5 tuple, meaning that there are 5 things that the sets or that the elements are drawn from in order to do things. And then the predicates are often written so that we can actually do them. We have to have a set in order to define a predicate, where we say for every element of the set of reals, x squared is greater than or equal to x. In this particular case, that is a true statement. I did not put the cubed in this time, so we can say, long arrow, we can say that's true. Finally, what do we do with them? Well, we do operations on them, and we're going to be doing these in the programming assignment. So, and I've got some slides towards the end, or at the end, that we'll look at it. So we have the union, where I combine elements from different sets. The intersection, where I take only those elements that are common to all of them. The difference is those elements in the first set, but not in the second set. And then the symmetric difference would be those elements that are in one or the other set, but not both. And finally, the complement. And all of these are operations that you'll be performing in the programming assignment. And we'll talk about those specific operations in about, about 45 minutes or so. Function then, since we've been talking about sets and we've been talking about Cartesian products, a function is a subset of the Cartesian product of two sets. What does that mean? If I have two sets, what do I have for the function? A two-tuple, which we also call ordered pairs. A function is defined by the ordered pairs, that one value produces another value. Now there's a restriction on that, and that's what makes it a function. We can call it a mapping or transformation, but the idea is that I take one value from the first set and I produce a value in the second set. So given two non-empty set, each element of A is assigned to, and I probably should change this color to red, exactly one element of B. That's what makes it a function as opposed to a relation. For a function, if I give you a value of x and say, I've got a function, let's write big so that it might actually, the people on, is there anybody on this board? I should probably check. nobody's going to get on. I'm not, no, just me. Oh no, there's somebody on. Okay. So let's say that I've got this one doesn't work much better. F of x is equal to 4x minus 32. So if I give you a value of x, let's say x is 3, how many values of the function do I have? It would just be one. What if I had, let's see, f of x is equal to 4 times the square root of x minus 2. Square root of 3. I said x and I wrote 3. Is this a function? Well, let's try it. Let's say x is equal to 16. F of x is equal to 4 times 4 minus 2 is equal to 14. However, f of x for 4 is also, or 16 is also equal to 4 times negative 4 minus 2, which is equal to minus 18. Go back to your algebra days. Is this a function? No. Actually, I've got a daughter, and she's a sophomore. Sometimes it's hard to remember. They grow up so fast. I've got a sophomore right now that's going through this kind of thing, talking about, is it a function, is it not a function, how can you find the minimum and the maximum and all that kind of stuff. You've done that before. This is just looking at it from the standpoint of each individual item has to be a discrete value, where we're taking them from one set and putting them to another set. So in this case, we do not have a function, we have an equation where if I take something from the first set, I'm going to have multiple values in the second set. And it's not going to be defined for some value. All right. So the way we write them is we usually write it that f of some value is equal to another value, where the first value is from the first set and the second value is in the second set. There must exist, note the exclamation point, there has to exist a unique value of phi. We can't have two values like we do here for the second example, 4 times the square root of x minus 2, because if I give you an x, you can't tell me which phi value you're going to have. So to be a function, it must have that property that the second value is unique for each value from the first set. Another thing that is usually applied to the word function, and in general this is true, it must be everywhere defined. Why do we talk about this? We talk about this because, believe it or not, you'll have an exam to get your associate's degree that will also talk about this. Forgot to plug in my computer. Hopefully it will live for another day. But here it's simply saying that my set A must have values for everything in the set. So here, if x is coming from the set of integers, does it have values everywhere in the set? Let's say x is the set of integers and the resulting equation is result is the set of real numbers. Is it everywhere defined? What's the square root of negative 16? Not in a set of real numbers, so it's not defined at that point. It's like having, another one that we use all the time is dividing by x at some point. When x is 0, is that defined? No, it's not. So while we would normally consider it a function, because it's not defined at some particular point, it is not a full function. It's in fact what we would call a partial function, where it's only defined over a portion of the first set, the domain. So I thought I should probably move those two terms a little bit earlier. I think I've got them on the next slide. But we define the first set as the domain of the function, and the second set is the range of the function. So any function or any formula that is not defined over the whole thing is called a partial function, as opposed to a function. This distinction is important because there are other people who teach 2130. We all have input into the exam you guys take for your associate's exam. And you must understand that to be a function in general, a general function, it must be defined over all elements of the set. So if I were to define it as 1 over x for all integers, then obviously it's not defined at 0. That would mean that it would not be a function. It would be a partial function, but not a function. So hate to put that on you. Knowledge is a dangerous thing, but that's it. It's just a fact of life. So if it's not defined everywhere, we call it a partial function. And here's the example. F of 1 over x is not defined everywhere because, as we stated earlier, it's not defined for the value 0. So as a result, it's not, in general, it would not be called a function. It would only be called a partial function. You'll find I don't really ignore that. I will treat it as a function most of the time. And in your programming assignment, I'm fine with dealing with partial functions there. Just understand that mathematicians can be very much sticklers for the no doubt about it, the terminology must be absolutely correct. If I use the word function, then it doesn't apply to it in this case. But in general, in practical cases, it applies all the time for partial functions. We still would term it a function. And once again, the set A that we're taking the first element from for our mapping is called the domain, and the set that B comes from is called the codomain or the range. Range is probably the more common term for it because it's one thing to have a three-syllable word versus a one-syllable word, and most people like the one-syllable words more. Range is more common, but codomain is the technical term for it. And the other thing is, what's the relationship between A and B? Are they always the same set? Are they even always talking about the same type of thing? Do they have to be numbers? No, they could be any set. I could have a function that, let's see. I don't have much room there. Sorry, you people on the recording, you can't see what I'm drawing on the board. But I could, I might as well put it on the slide. But I could say, for example, that A is the set of people, and that B is the set of homes, and that F of A is the function that maps A to B, where B is the primary residence. Now, for tax purposes, you need to actually have a primary residence. In other words, you can't just say, oh yeah, I've got a home in Florida, and they don't have income tax. And I may live all year in Utah, but my residence is in Florida. So primary residence here is where you spend most of your nights, typically. So this would be something where it's not numeric. The set A is the set of humans, people on the planet, and the set B is the set of domiciles or homes or houses. The other thing about this particular function is it everywhere defined? And unfortunately, there are some people that have no home. So no, it's not even everywhere defined. There are some other issues. Once we start getting outside the range of numbers, there are some oddities that we'll see. So we usually talk about these in terms of numbers, but we can apply it anywhere. We can apply it to this. Let's see. We could say that A is the set of books, and B is people who have read, no, not people. This would be a set, never mind. That was an interesting idea that is taking us somewhere we don't need to go. So let's instead take a look at how we represent functions. Picture, as they say, a picture is worth 1,000 words. I'm going to try to keep it shorter than that. But we've used Venn diagrams to talk about functions, or not functions, but sets. And since now what we're doing is we are taking elements from one set and mapping them, transforming them, or using a function on them to produce a value in another set, then we can use Venn diagrams and simply draw arrows from one set to the other set. This is useful, especially if we can enumerate or talk about the specific elements in the set, if we can count them, if it's a small enough set. Venn diagrams actually become pretty easy for us to do. Set my do not disturb on. My children sending me text messages. But there are other times when what we'll do is we'll actually line them up to show something or some property of them. In general, we're going to be using it, we're going to talk about composites of function, where I apply a function one time and then apply another function or the same function to that result. But we can also use this to tell something about, for example, the domain and the range sets, once again, if they're fairly small. A general function is one where it doesn't necessarily have any given property. And then we have functions that display specific properties. For example, an injection is one where every element of set A has, let's see, an injection is also called a one-to-one. Every element here maps to a unique value in the set B. So, in other words, I don't have here, I've got two elements in set A for the general function that map to the same element, the third element of the set B. So does not have some unique value from the first set A that maps to it. But here in an injection, that is the case. In this case, it's also not surjective. Surjective means every element of B has at least one element of A that maps to it. Most people don't talk about this as a surjection, they call it onto. In other words, we're covering the entire set of B. A maps onto B, and that there are no B's that are not included. Like up here, for example, I've got X and Y, and in this particular case, we're saying that f of X only maps to a portion of Y, so that would not be onto. So our surjection is onto, in this case, if A has more elements than B, then obviously at least two of them have to go to the same element. And then finally, bijective is both one-to-one and onto. And as a result, every A has a unique B, every B is mapped to by a unique A. And what we'll find out is that's actually what's called a reversible function. Some other things, some other representations, we'll often use formulas. F of x is equal to 3x plus 2, or for those of you online or later on watching this, the one that I had earlier was this is not in general going to be a function. F of x is equal to 4 square root of x minus 2. It's not a function on integers. But is a function on n and z plus. So sometimes we'll have equations or formulas or things like that where in general this is not a function because there are two values for any given value of x. One of them is a positive number, one of them is a negative number. But if we restrict the set A, it can restrict our domain and we can end up with multiple values there. Special functions we use in computers, one of them takes real numbers to integer numbers. For example, and these still don't, I'm not positive why we still talk about these other than it is an objective for your 2899 exam. But I know all of you have heard the term round. You round a number. What do you do when you round a number? Let's say I've got 3.1415926. I can't go much beyond that. In school they never had us memorize the first 100 digits of pi, which both of my daughters have done at one point or another. Well, they both memorized around 70 to 80 digits, and at that point it's like, oh, forget it, it's not that important. 3.1415926 is how far I go. If I round that, what do I get? 3. Why? What's the rule for rounding?
Smaller than 5, you round down. 5 and up, you round up.
If it's at the halfway point, or if it's less than the halfway point, I go down to the largest integer that is less than that. And if it's at the halfway point or greater, I go up to the next higher integer. So if I've got a number with a fractional part, that's how I do it. The floor is one where all we really do is we just say, I don't care if there is a fractional part, I'm going to take the largest integer that is not greater than this. So in this case, if I had 4.9999999, the floor of that is 4. Have you heard the word truncation or truncate something? That's oftentimes the word that will be used in place of 4, especially if you are looking at like getting rid of digits after a particular point. Floor is specifically a real number to integer thing. But what if I just wanted to say, I want a real number and I only want the first 3 decimal points? I could round, and in general with formatting in computer languages, that's what they do, is they'll actually round that. But what if I just want to cut it off? That's called truncating. So, when you truncate, you just ignore everything after a specific point. If there are other digits, then you just say, those aren't important enough at that point. It's one of the reasons why we talk about significant digits, is at what point, if I have 1.00000 with 20 zeros and then a 3, how important is that 3 for computation? It's 20 orders of magnitude below the 1. If I multiply 2 times that, what do I get? 2 with 20 zeros and then a 6. Is that 6 going to be important to using the value 2, or is 2 close enough? Can we truncate at that point? And that's why we talk about the significance of digits and how they affect the resulting computations that we have. We'll talk about that a little bit more, because when we get into representations of numbers, what you'll find is that there are some numbers we can't represent it accurately, and when we perform computations with those, we end up with errors, and we can propagate those errors through the operations we do inside a computer. Because inside the computer, we're using binary, we may not be able to represent, for example, 1/10 exactly in binary. 1/10 is an infinitely repeating fraction inside in binary notation. So if you can't represent it exactly, and so you get a growing error as you continue to use that within the computation. Anyway, the other one that we have is ceiling. As you can imagine, if I'm talking about the floor, I'm talking about the largest integer less than, and the ceiling would be the smallest integer greater than. So if I have 1.1, the ceiling of that is 2. It's bigger than 1, so it's got to be the next integer value. Is really all it is. It's how, what's right above it that we're not quite to. There are other properties. We looked at these on the previous slide. Now we'll have a formal definition for them. 1-to-1. For every element of the codomain, there is a unique value in the domain that maps to it. In other words, I don't have 2 values that map to a specific value in the codomain or in the range. So if I were to look at it on a piece of paper, essentially there's no repeated y value. If I start graphing my x values, I don't have any place on my graph where y is repeated, would be the kind of the way to look at it. So just as for the unique property for functions, I don't have any place where x maps to 2 values. Onto every value of b, or the codomain, must have a value from the domain that maps to it. And what this really means is that there are no bounds to my range. In other words, if my range goes from in this case, my upper hand to my lower hand, everything in there has something in it. So it has some value that maps to it. So there can be multiple values, but there's at least one for every value in the range, or in the codomain. And then a bijection is one where both of those are true. It's both 1-to-1 and onto. And the only time that can happen is when the cardinality of the sets are the same. So can I ever have a bijection between the set of integers and the set of real numbers? No. Why not?
Your real numbers aren't 1-to-1.
Real numbers are bigger. That set has more elements in it. So if I map from integers into the set of real numbers, I can't have a function that will do that. And if I have a function like ceiling and floor that maps from reals to integers, that means that I've got multiple values in my set of real numbers that map to a single value in a set of integers. So rounding does the same thing. 3.2, 3.25, 3.254 all map to 3 with both ceiling and with rounding. 4.9, 4.91, 4.9 cs2130.92 all mapped to 5 with ceiling. As a result, it wouldn't be, at that point, it wouldn't be 1-to-1 in that, or pardon me. Yeah, it wouldn't be 1-to-1. So it would not be a bijection. It could be onto all real numbers mapped to an integer value using either ceiling or round or floor, but it would not be 1-to-1 at that point. Not reversible. Some other or invertible. Other things, function f is invertible. In other words, we can take the inverse of the function and apply that to b to get the value of a. Well, to do that, it has to be a function and it has to be 1-to-1. It has to be onto and 1-to-1 to make that happen. All bijections are invertible, and it must be a function must be everywhere defined. Is the other thing that you may see somewhere. For every x, there's just an element of x, and there exists a y element of y such that f of x is equal to y. That means everywhere defined. Every x has a value of y. And here's one. If x and y are the elements of the reals, f of x equal to 1/4x equal to y. I'm going to have values of y, but it's not going to be a function. So why is that not a function? No. Why isn't that a function?
It's not defined in 0.
Yep, no value of 0. So because I don't have a value defined at 0, it's not a function. And then that would be called a partial function, and we've talked about that as well. We have not yet talked about composite functions. So given two functions, f of x equal y and g of y equals z, then if I apply f of x and get a value of y to put into the function g, then I can now make a composite or a more complex function, combine those two to produce a function that goes from x to z, as opposed to simply having two separate functions. And it's the function that you do first that's farthest to the right. So if we have functions on a set of integers, for example, f of x is equal to 3x and g of x is equal to x plus 5, then the composite function here would be
3x plus 5.
3x plus 5. G circle f equal to 3x plus 5. But there can be 4 f of x. So the composite of f, given f, would be 3 times x. That would be 9x. F circle g would be g of x is x plus 5. Multiply that by 3, we get 3x plus 15. G circle f is what most people think of, where I've got 3x plus 5 as my result. And then my final one would be g of g, or g circle g, and that would be x plus 5 plus 5. Those are the different composites that we can do. The ones that we're going to be investigating the most are going to be our end ones here, f circle f and g circle g. And we're going to be looking at those yeah, we're going to be looking at them now as opposed to later on because we're looking at the powers of, or it might be relations. I don't remember. 4 classes. Sometimes I don't get far enough ahead in terms of what I remember. We do talk about them. I don't remember when. But what we're going to be doing is talking about closures. And actually we'll get into that with relations as opposed to functions. But what we can do is we can apply this multiple times and find out, what values we might end up with a relation as opposed to a function. And a relation doesn't have the restriction that every x must have a unique value of y. That's the only difference between the two. And it doesn't have to be everywhere defined. So we're going to be using this composite when it comes to relations, and we'll use it to talk about, in particular, the one that's probably the one that we apply the most is what's called the transitive closure. So if f of x is equal to y, and then f of y is equal to something, and f is equal to z, and f of z is equal to a, and whatever, if we apply the function a whole bunch of times, what do we end up with in our relation or in the things that we're trying to talk about? So that's our intro to functions. We'll talk more about that next time, including the program associated with that. But you guys have another program that you're probably more interested in right now. So what program is burning the hottest? Not quite 45 minutes. So it's like more like 35 minutes. Program 3. What we're doing here is we're using an integer to represent sets. So actually I will give you, I've got some code that actually looks at creating a set of fruit using an integer to represent the fruit. So I came up with, I forget how many, 21 or 30, it might have been 32 different fruits. And I simply put them in an array, and then I can have a set where I say, okay, which fruit do you want? You choose, and that adds it or sets the bit in the integer that represents the set. But here, you're probably most interested in how we get numbers in, how we print the set out, and how we perform the operations. I think I've already mentioned that if you end up with a program that's more than about 50 lines long, you've done too much. So concentrate on the fact that the set itself is going to be an integer, and all you're doing is manipulating the bits within the set. So here, reading it in, we're going to be reading in 2 sets because we're performing operations on the 2 sets. Union, intersection, difference, complement of 1 set, and the symmetric difference between the 2 sets. So there's only one of them that uses 1 set, the other one uses both sets. So here I've got some pseudocode for a function that will read in a set and return the value. So that means for my main program I'd say, please enter set A. And then I would call this function, and whatever value comes back from it, I would assign to a main program variable called set A. You can do this can you do it in Java? Can you write a function that returns an integer in Java? Yeah. Can you do it in C++? Can you do it in Python? Yes, you can. This pseudocode will fit all 3 languages. So it's only a matter of translating. How do I read in an element? I've got system, let's see, system, it's not system out. It's a scanner in Java. I'm not a Java person. Next int, where you read in the element. Ask, how do you ask for something? You print something to the string. So I could do, if I was doing it in C, I'd have a printf. Please enter element I, where I would be a field. So let's take a look. I'll do this in C++. You want me to do it in C or C++?
C++.
Shocking, I tell you, that anybody would want me to do it in a programming language that they could probably program in. How many of you have completed 1410? Okay. So, not quite there yet? So, are you Java programming? Oh, okay. Yeah, so hopefully, when I teach this class, I allow you to program in Java because people can take this class early, and now Python because people can take Python as well. But one of my goals is to also help you become more sophisticated in whatever language you're programming in. So that's kind of one of the key things here. So we're going to create a function. Do I need to have any data coming into the function? I mean, I could. I could, for example, send it a string that says which set you're reading in. But that's kind of, it's overkill for what we want to do. In my main program, I could just have print out a message that says, please enter the set A. And then I could call this function and read it into set A. My main program would tell me which set I'm reading in, as opposed to my function. So I'm going to keep my function free from any ties to which set it's reading. So what I would need is get my color here, we'll do it like this. So I'm going to have an integer function, or a function that returns an integer. Java, C, and Python. I remember, Python does not tell you the type of thing that it's returning. So of those languages, it doesn't have this kind of declaration. You have a definition statement in terms of what's going on, and your return statement is the thing that determines what kind of thing you're returning. So this would be a C++ translation. And this would be read set. And inside here, do I need anything? Void means I don't have anything in there. I could just leave the parentheses there with nothing. The compiler will operate well in either case. But I do need the parentheses because I'm declaring a function. And inside here, what I need, okay, I'm going to have to declare an integer to hold the set. So I have an int. Set. I can even initialize it, which is probably a good idea, to 0. Out of room now with my comments. So I'm probably writing too big. All right, the next thing I need is I need something local to hold the number of sets. So I'm going to declare, I'd like to declare things at the beginning. I'm old school. What you have to realize is those of us who have been around for a long time and have used functions that are sometimes large, like several hundred lines of code, understand that needing to search through to find a declaration for something can become tedious, and sometimes it's hard to see, oh, you're declaring something on this line. It's not just a line of code. So we usually, old school is declare everything up front. New school, and I've done some actual searches on this just because evidently the common pattern now is to, generally speaking, declare something close to its first use. That can be somewhat confusing, especially if it's used for several hundred lines of code. You then have to start doing searches on where the declaration is, what type of thing it is, when you see it used somewhere. People don't often comment or code the way they should. So, I will comment on these types of declarations in your code, but that's about the extent of it. So I've got 3 integers I'm going to need in here. So that's kind of, not only do I need to declare the integer for the set, I could declare the other integers where I'm reading them in and doing other stuff, but I'm just going to declare them at the front so that you know where they are. So I'm going to ask, when I print something in C++, what's my command? Cout. I'm not going to do the standard : : I know some students have said that their instructors have told them you should do that all the time. I'm a comp sci person. I'm lazy. Something as common as standard, I think, it's overkill. It's pedantic. That's the 25-cent word for today. It's pedantic. You're following the rules much too strictly when you do that, and you're wasting time on things that are really fairly clear to most people. So cout, nline, those kinds of things, cin, having the standard there. I'm going to do a using namespace standard in my code so that I don't have to do that. But here I just do a cout. Number of elements. But I need to know, so I'm going to ask in a semicolon. So I'm asking how many, it's going to be on the same line as everything else. The next thing is I'm going to read it in. So I do a cin, and I'm going to read into num_l. And then the next thing I'm going to do is I've got error checking. This is error checking. So just out of curiosity, let's say I put in the number 5, or the valid numbers I have are 0 through 10. If I put in the number 5, how many times will this while loop execute? Pardon me?
5.
Number of elements less than 0 or greater than 10. Is 5 less than 0? Is 5 greater than 10? So the condition doesn't hold. How many times do I do the body of the loop? Big 0. I don't do it. It's kind of like an if, except I've got a while. Just in case somebody can't get it through their head, I need a value between 0 and 10. I can have 0, I can have 10, I can have anything between there, but if you give me -1, that's bad. So I'm going to ask you again. You give me 11, that's bad. I'm going to ask you again. So that's what this does, is it says if it's outside the range, so only executes for bad values. So that's the kind of thing that we can do. If I used an if, what would be the problem with that? Instead of a while, what if I used an if?
Again, it won't run in the
One thing you must be aware of is that people who are at the keyboard typing, like me, sometimes don't really read the prompt and can enter bad values multiple times. What this will do is protect your code and keep you from trying to use a bad value. Now, I'm not going to ask for 12 values, no matter what you do. 12, or the thing that happens to me sometimes on my keyboard is I'll get key bounds. I meant to enter 2 and I get 22. So, those are the kinds of things that we're trying to prevent. So here, very simply, we'll do a while. Num_l is less than 0. For my OR, what kind of OR do I need? It's with the, pardon me? Yeah. The two. Logical. Yeah, especially if I was using Java, Java does not treat numeric values the same as it treats integers, so there can be some issues there. All right, so I've got my curly brace now. What am I going to do inside here? C out. Bad user. 0 to 10. Enter again. So not necessarily the best error message, but I'm running out of room, so I can't write error. Please enter a value between 0 and 10. Would be probably the most and then value. So, and then cin. Number of elements. So this gives me my error check. That's my loop there. And now we could either use a while loop or a for loop. I've written it as a for loop here, which is why I needed the integer I. If I didn't want to use the integer I could use a while loop and just decrement num_L until it's equal to 0. As long as it's greater than 0, I would go through and do stuff. When it reaches 0, I'm done. Your choice. I will allow you to do it either way. But here I just had for I equals 0, I less than num_L, I plus plus. So we're just doing a initialization. Like all for loops, we start with an initialization. We have a check in the middle or a condition for the termination, and then we have an increment or a change to our loop control variable. Except it doesn't have to be. We could actually leave any one of these or all of them blank if we wanted to. But here, I have a C out. I've got my curly brace, C out. We always like to make it good for people who are using our program. Nice and neat. They can enter stuff on the same line and we're okay. We'll read the element. Ooh, I need one more thing in here. Value. And that's going to be the value that we read in from the keyboard. Or I guess I could use element, appears to be what I've used in most of the place here. But I'll use value because that'll match the PDF that I gave you for how to compare everything. So I'll do that. I'll have another while loop. While value is less than 0 or value is greater than 9 in this case. So I've got a slightly different set of conditions here where I have to check for 9. 10 would be the number of elements. I can have 0 elements, but here there are only 10 possible values. So I have to have the digits 0 through 9. I have a curly brace, which I can't place there because I write too big. Let me write it just a little smaller here. Value is greater than 1. Write my curly brace, C out. And I'm not going to fill all the details in. And now I'm going to finish it up over here, because I've only got a couple of things left, so I'm going to finish it up underneath. So now I'm down to add the element to the set. How do I add the element to the set? I initialize the set to 0. Which is the empty set. In other words, a 1 indicates that there's something there. So how do I set something? Any ideas where I can go to? Man, tough room. Sometimes I feel like a comedian, standing at the front telling jokes and nobody's laughing. It's like, oh my goodness. The room, I'm dying out here. Dying, I tell you, dying. Okay. If we go to the link inside the programming assignment. So here's our programming assignment. Sorry, it's going to look weird for a second. Link inside our programming assignment. Go to this document. And come down here. To set a bit, we have set A is equal to set A bitwise OR with 1 shifted by value. Look like a good way to do it? Yeah. Need to get my computer to cooperate. Over here, over here. How I got that smart, but it did. So what I'm going to do over here, and I'm going to add the set is equal to. Actually, I could get really fancy here. B set bitwise OR equal. Yes, you can do that. Bitwise OR equal 1 shifted left by value. And let me put this underneath. One shifted left by value. A little comment there. Those are the same operation. It's the same thing that we have. So I added the element. I'm then going to have the curly brace. This is the end of the for loop. And then all I'm going to do is return the set. And there we go. So almost completely ran out of room, but not quite. So mostly because I just write 2-bit. So pseudocode. What is going to change on this right-hand side for Java or Python? The input and the output. Printing things to the screen and reading the keyboard. And the header. That's really the only, and the fact that Python doesn't do integer declarations. Other than that, this is code in all of the languages. So they're all based on C, And as a result, they all use C-like syntax, especially for loops, while loops, and everything else in between. The other thing is the Python doesn't have the parentheses kinds of stuff, so the loop could look like for I in 0:9, or not 0:9, in range num_L would be the way that you'd say it in Python. There are a couple of subtle differences, but the concept is pretty much identical. So that's why we can use pseudocode to describe it, and it fits all the languages. If you know how to do something in the language, you use the pseudocode to be able to get through and do it. All right, so now we know how to read it in, how can we print it out? Yet another thing, what we want, we just want the set. We don't want, all the labels and stuff like that, because we're going to be doing this like 5 times. The label's going to change every time. I don't want to include the same code 5 times, 6 times, 7 times in my program. That doesn't make sense. I mean, why would you copy and paste and just change like 2 or 3 things here and there? There's a something reflecting light, making an image on the bright spot on the back. So what I've got here is something that will print out a set. And all it prints is the curly bracket, the numbers separated by commas and spaces, and then a closing curly bracket. Once again, this works in Java, Python, C++, probably the pseudocode will work in any language that you can perform the operations in. So for this one, it should take an integer input as a parameter. So what we'll do, and this is also very similar to the homework, where you're printing out the bitwise representation of an integer. You'll note it's very similar. But here, rather than going from 31 to 0, we're going from 0 to 9. So that's really the biggest difference. And rather than printing a 0 or 1, we're printing the number I, which is the element of the set. And if it was fruit, we'd be using I as an index into an array that contained the names of the fruits. So here, do I have to return anything from this? Nope. I'm not bringing anything back. So C++ translation. No, I'll have a void. Print set takes an integer as an argument. I need to declare a Boolean, and I have a loop control variable. So here I'd have a bool, comma. I initialize it to false. And I have an integer I. Loop control variable. Okay. So now I can start the rest of the stuff that I have. So here I'll have a print an opening curly brace. See out. Curly brace. I'm worn out. That's too much work. It's not too bad at this point. And then we can do a for I equals 0. I less than or equal to 9. I plus. And inside here, what I need to do is check if the bit is set. So how do I check to see if the bit is set? Where can I go to find such esoteric knowledge? being more than a little silly about the whole thing, but if you come down here, to test a bit, we have if to set it we do an or, to test it we do an and. We just check to see if we're going to be using I instead of value, and we'll shift 1 by I. I will start at 0, so we'll check bit 0, then we'll check bit 1, then we'll check bit 2. And we'll check to see if that bit is set. I need the greater than or greater than 0 here if I'm using Java. If I'm using C++, all numeric values, all integer values are actually treated as true or false. So here I need the if be set ANDed with 1 shifted left by I, and we'll go ahead and make it Java compatible. Greater than 0. What does greater than 0 mean? Greater than 0 means it was we're checking one bit. What can it have? It can have a 0 or a 1. So if it's greater than 0, I haven't shifted the result here. That's the big thing. Because I'm shifting this bit over by 1, or by some number I, when I'm checking 0, I'll get a 1 or a 0. When I'm checking 1, I'll get a 0 or a 2. When I'm checking 2, I'll get a 0 or a 4. This will return an integer value, and it will check the ith power of 2. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16. We go up to 2 to the ninth, which is 512. So at that point, I'm checking to see if that bit is a 1, and it will return a value that will be greater than, either equal to 0 or greater than 0. So that's all. That's the reason why we're checking the greater than 0. For C, 0 would be false. Anything else is true. I'm trying to remember. I wrote Python for this last time, and I think Python does the same thing, but I don't remember. Try it in your language. Java requires the greater than check. Because Java is strongly typed, it requires Boolean expression. It must be specifically Boolean. It can't return an integer for the if statement. And that's the reason why you need the greater than 0 in Java. Java is a strongly typed language. So that is the if bit is set, if bit I is in the set, so that's the REF statement. Then I check if need comma. The first time through this is comma if comma true or need comma true. Goodness, going through code is very difficult. Is need comma true. Not the first time. I set it equal to false on purpose the first time because the first number I print is the first element of my set. Do I want a comma equal or a comma space before it? No. So that's that is the only purpose of need comma. We want a pretty printout. I don't want to always print a comma space after because what if it's the last element of my set? We do wind up with a comma and a space at the end of everything, and that looks horrible too. So we're trying to be neat about our output. So if there is a need comma, I would have a C out, comma space, and that would be the end of that if. Otherwise, I'm going to print I, to C out, I, and then I set need comma to true. That means after the first number, I'm always setting need comma to true, but that's okay. I think it's all lowercase. Anybody remember?
For the true and false, yeah, it's all lowercase.
Yeah. And I think it's Java that uses the mixed case. So there we go. Then I'm at the end of my outer if. I'm at the end of my for loop. And then I'll have print the closing curly brace. Curly brace. Semicolon. And then I close everything off. I'm not returning anything, so I'm done. So the idea is that we want to be nice and neat for our people. We just don't want to put a space between everything or have extra spaces anywhere. You'll find that probably the worst thing you will have to do in your entire time programming is either writing input or output for humans or trying to fit a specific format required by a device somewhere and sending things over the line. It must fit a specific format. That is the most tedious programming you end up doing. Everything else is not too bad. We got 16 minutes. We should be able to get through this. So now the question becomes how, let's say that I have, so in our main program, we'll have int set A, set B. And at some point we will call set A equals read set and set B equals read set. There'll be other things in there. For example, before we call read set, we'll say please, and we'll output, please enter the values for set A. And then before we call read set for set B, we'll say please enter the values for set B. Very straightforward. It's just a way to get the person to understand, oh, you're trying to enter values here. Please do not vary from this input. I actually use a script for grading, and if you break the input, it breaks my script, and I end up taking like an hour or two just grading your program. So I would beg you please to fit the format, the method that we have here. So now I've got set A and set B. How can I compute the intersection? Do I have to go through bit by bit and have a for loop and check the values and then set the value in the resulting set and everything else? No. What operation is equivalent to intersection? Intersection is where an element is in both sets.
It's
An AND operation. So here I could do a Something as simple as that. I've now done my intersection. I use a bitwise and. It computes the result and sends that as the parameter to the print function. So I don't even have to declare a variable to store it. I just send that operation as the parameter value. How about union? If intersection is and, union is or. Well, we could do set B first. It doesn't really matter. Bitwise again, because I want each individual pair of bits. So bit 0 compared to bit 0, bit 1 compared to bit 1, etc. So I want that kind of comparison there. How about the complement? Now we're only doing the complement of set A. We don't need to do the complement of set B. You can print it out if you want, but I don't look at that one. Anybody remember what or know what the complement is? And we'll do a quick search.
Is it all the zeros instead of all the ones?
Yeah, we want the ones to be zeros and the zeros to be ones. So here, complement operator in C++, Java, and Python. Because I don't think anybody's going to write in C. Bitwise complement operator. The bitwise complement is a unary operator, works only one way, denoted by, oh look, a tilde. And believe it or not, it's tilde in C++, it's tilde in Java, it's tilde in Python. So tilde, 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 tilde is the operator. So here we would do print set tilde set A. Difference is our most complex one. What is the difference? Those things in set A that are not in set B. How do I get the things not in set B? Tilde B, tilde set B. How do I find out where things are common? I do the intersection, the and. No, sorry, that's capital. Should be, I think I wrote it camel case. I try and do camel case because you guys have been taught camel case. Set A anded with tilde. Now, as you know, a unary operator is usually the highest precedence. So I'll do the complement and then the and with set A. And then finally, our symmetric difference, things that are in one but not in the other, they're in going both ways. In other words, in set A or set B, but not in both. Sounds like begins with an X.
Exclusive or?
Exclusive OR. It is an exclusive OR operation. And there we go. The symbol for XOR in Python, it's actually the same in C, C++, Java, etc. It's the caret. You guys still use caret? What is there another? You have another name that you use for it?
We just call it a carrot.
Yeah, we always called it a caret. So I don't know. I am a dinosaur. Sometimes dinosaurs don't know how things happen to it these days. So print. Just ask my kids. So, Dad, you're old. Set A. Exclusive OR. So now all I have to do is put a line before these that says, C out, the difference, set A minus set B, is colon, then call print set, then have a C out with an end line, or a string with a backslash n, new line character in it. So the labels can come from your main program. As you can see, I've got 5 function calls here. I need probably 2 lines of output, one before and one after each. Actually, I could even combine them and just add a blank line before that one and a blank line before the others. So it looks like maybe 10 or 15 lines here, and then the 2 functions, and then the word main, 2 declarations for the integers, set A, set B, and a return 0 because you have to have a return value for at least in C++. So your main program now becomes print a couple labels, call read set, and then print a label, call print set with a function, with a value inside of it, call label, print set with function inside of it, or an operation inside of it, and you're all set. It's about, like I said, it's about 35 lines or so, plus comments, a few comments. So 40, 45 lines at most. So if you get over 50, you got to start wondering how many comments you're putting in. But if you're trying to do it with an array, I have seen people try and do this with an array of integers or with set operations, and they've produced programs that were 250 lines long. And they spent a lot of time working on it that they didn't have to. Because the thing that we're trying to do, we're looking at sets, but we're looking at how can we manipulate bits to our advantage to represent that kind of thing. And just to give you a quick idea, sample, homework 3. Oh, binary representation. The sample. Another, where I went through that's actual homework. I'm looking for the example. I did have an example, and I don't remember where I put it, for using fruit. As a set. I'll find it and I'll post it. Essentially, all you have to do to use this to represent something other than the integers 0 through 9 is use the set number as an index into an array of whatever. It could be a record of people's names. It could be an array of fruits. We're using strings. It could be, whatever you want. You're basically just drawing a distinction between a bit and an integer with some other value, and then you'd have an array of those values. So, not rocket science, just computer science. And like I said, we use bits all the time. We use them for communication. We use specific bits in order to indicate what's happening in TCP/IP communication. We use them for error correction and detection. We do manipulations of bits in order to figure out the error correction codes and what kinds of things we might need to do there. To look at parity, we have to look at the number of bits and count them. We use bits for allocating space on a disk drive, figuring out which portions of the disk drive have or have not been allocated. So every time you store something on your drive, the operating system is looking at specific bits in order to determine where to store something. So this is, depending on what level of programming you're at, you may use it a lot. If you're at a high level of programming and you're simply programming user interface or web apps, you're probably not going to be using bit manipulation very often. But if you're programming driver software, communications software, operating system software, if you're doing PLC, that programmable logic controller programming, for example, I do know, I had one student in Texas that he didn't finish his degree. I was a little disappointed in that because he was really sharp. He was a Navy guy, worked at the NSA in San Antonio doing reverse engineering on malware. But when he got out of the Navy, I got him a job as a PLC programmer so that he didn't have to flip burgers to finish his degree. And he ended up working so much and making so much money. He was making, I know he was making at least 70. He was probably making, by now he's probably making 150, 200,000 a year doing PLC programming for oil and gas companies, electrical companies, manufacturers. They use PLCs to control processes like curing carbon fiber for, not for undersea submersibles, but for aircraft. So those are the kinds of jobs that are available if you don't feel like I want to develop the next web app in order to do something. So there's a lot of different things going on, and understanding how the bits can be used in order to make that happen, I think is an important capability, and sets are a good place to just say, we can represent a set of 10 things using 10 bits. All right, I think I've abused you enough. Written most of your program 3 if you're using C++. If you're using Java, you've got a couple of things to do. You have to do the system out.print, system out.println, whatever your scanner name is with nextint or other stuff like that. But in general, it's just the input and output that are going to differ between each one of the languages. You guys have a good Tuesday evening. I was lonely last night. Maybe somebody will be on tomorrow and need some help with something. But no programs were due for any of my classes tonight or last night, so nobody came on at the 9 o'clock help session for anything. Other than that, you guys have a good one. I'll see you Thursday morning.
Thank you.
Thank you.
Thank you. Thank you.
You bet. Online guys gone.